So in our technology history, we have a very well-known pair of brothers, Wilbur and Orville Wright, who are the first people in our continent to have flown. So that was in December 17th, 1903. And what happened is that they actually did a coin toss because they wanted to know who would actually fly first. So Wilbur won, and so he started. And unfortunately, the plane stopped and it stalled, so it could not go further. And Orville actually made the first flight, and that was on December 17th, so 3 days later. And that flight was about 12 seconds and 120 feet. So as you can imagine, that was really quite short as a flight. So this is just to tell you where things started. And today we are quite a long way away from this, because we could, as you can see, fly for 20,000 years without having an accident. If we did not stop, but we flew continuously for 20,000 years, statistically we would have no accident. So it means that we can safely fly during our life, and most likely we will not have an accident. And that, as a matter of fact, if you look at the number of accidents per departures, you see you have approximately today 1 per 1 million. So every 1 million planes taking off, you have one accident. So it's really very few. And if you look at what happened over the years, you see that the number of accidents is really decreasing significantly. And that usually these accidents are due to human error. They are not due to something else, right? So there are plenty of examples of this. So originally we were really working from intuition and theory, and we were working from experiments as well. So, you know, this is here the notes that the Wright brothers had. This is in Franklin Institute Science Museum. And this is Wilbur's handwriting. So you see here that he thought at some point that you should have a square section for the wing, or maybe at the end he thought about that section. And he did some calculations on the side to try to figure out what would be the best version of this. So I thought that is very useful to think about, because not only do we work from some sort of intuition, because the mathematics were not there yet, or we learn also from experience. So for example, this is the Comet aircraft, and as you know, it broke because of windows that were, instead of being rounded, they were square, and that created, of course, stress concentrations, and the whole thing broke down and created a convertible aircraft, which was not really in fashion. So as you can see, you have also bird strikes, which can completely destroy the engine. And all these things are very useful to know, because you cannot predict all of these things until they happen. And so now they are, of course, doing experiments on Rolls-Royce engines where they throw virtual birds inside the real engine to try to figure out how it works. And they also perform numerical experiments of that type of engine being hit by a bird. The other thing which taught us a lot about fracture is the Liberator ships. So this was during the Second World War. You may know that the US were bringing a lot of food to the UK using boats. And these boats were usually the target of U-boats, which were the German Nazi submarines, which were targeting these boats in order to get rid of the food and other things that were being brought to the continent and to the UK. And so, of course, these boats were very useful. They were built very quickly by women in the USA. So they were essentially welded together. So, you know, you can imagine huge pieces of steel that you see here on the right-hand side that were welded together using welds. And the ship was basically made only of these huge sheets of welded metal, and that's it. They were made very quickly, and they were put on on the sea very fast in order to take all the things that we needed in Europe. So that was a very good idea, and on top of that, because the boats were sunk so frequently, a lot of boats needed to be rebuilt. And what happened is very interesting. So maybe you wonder what could possibly have happened to these different boats because of the way they were built. So as you can see here, this is a welded construction, and you have a weld in the middle. And if a crack starts to propagate from the top to the bottom, for example, the weld here is not going to stop the crack. So the crack is going to be able to propagate through both pieces of metal. And this is something which is very typical and problematic, and this is what created the idea of rivet holes, because with a rivet hole, the hole is going to attract the crack, and the crack will be stopped by the rivet, and it will not start on the other side until quite some loading. So this is something that we learned by experience, that the welds are not good crack arresters. The other thing that was learned is that because of the U-boats, so the submarines that were targeting those ships, they were going more and more north, close to the Arctic Circle, in order to reach the UK. And the problem with that is that if you go more north, well, the temperature is decreasing. And when the temperature decreases, metals become more fragile, so they become more brittle, as opposed to ductile, which means that we have a ductile to brittle transition. There is a transition temperature, and if you are below the transition temperature, well, then these metals become more brittle. So the combination of having more brittle materials with having welded structures led to huge catastrophes with boats that were actually broken into two pieces by waves when they were trying to make it to the UK. So this is very interesting, and I think it's worth thinking about, that we learn from intuition, we learn from design, we learn from experiments, and we learn also now from science and mathematics and mechanics, but all these things took really a long time to be built. If you look at the terrible cases of shuttle crashes, again, these things happened because of very small and details, like in that case, it is believed to be due to one of the little squares on the surface of the shuttle, which was slightly off, and that created some sort of problem during the flight, during the takeoff, which then led to the destruction and killed the astronauts. And this was also due to very small, minute problems in the structure of the aircraft. Similarly, if you look at the Liberty Bell, which was in Philadelphia, people were wondering how to arrest a crack, and what was done is something that's quite counterintuitive. I mean, the bell was taken and a little hole was dug at the crack tip, because by digging a hole, what you can see is that you can decrease the stress intensity factors, you decrease the energy that's available for fracture, and therefore the crack will not propagate. So this is something really interesting also to keep in mind. So one of the key questions that you have when you work on fracture of homogeneous materials, but fracture of any material in general, is the question, when should a structure be inspected for flaws? So we can ask ourselves, how do we figure out when a structure should be inspected? Should we do it every flight, every millions of flights, every 10,000 flights, every 100,000 flights, if we're talking about an aerospace structure, for example? So these are the questions we want to address. And the question is, how are we going to address this? And one of the most simple ways to do that is to assume that a pre-existing crack lies in the structure. So this pre-existing crack is assumed to exist, and it has a certain size which is fixed by the design codes. Once you have that crack here, which is fixed at the beginning, the crack will propagate according to a certain type of rule using certain types of codes. This is very codified and done in very strict ways. For example, one of the codes that's used in the US by the FAA is called NASGRO or AVGRO, which is a code that will tell you, based on the principal stresses that you have in the plane where the crack is located, how many cycles it will grow, and it will give you an idea of the shape of the crack. So during my PhD, I came up with a completely new method, which was based on the extended finite element method, which is published in this paper here at the bottom right. And the idea there, it was to actually pre-decide on the crack, but let it grow arbitrarily, even if it wanted to grow out of plane, because these AVGRO and NASGRO approaches only allowed cracks to grow in plane. And they made very specific assumptions, which were that the whole path of the crack was computed assuming the worst case scenario in terms of fracture and in terms of loading. So we assumed that during the whole propagation, there was no release of the energy, that the stress being applied was the maximum stress that this section in the component would actually see. We did not, therefore, assume that there will be a release of the stresses due to the fact that the crack is propagating. So my method, which was designed by myself and my supervisor, Brian Moran, allowed us to look at much more realistic cases, which in fact led us to different fatigue lives and allowed us to make very nice work forward in that area. And now these ideas are implemented in commercial codes, for example, at Senairo in Belgium. The second question about how to look at fracture of homogeneous materials is how do you deal with the accuracy of your simulations? Because if you look at an homogeneous material, you have certain assumptions. So you will, in that case, assume that the fracture is linear elastic, usually for aerospace cases, because it is forbidden in these design codes to have plasticity. And plasticity would actually help dissipate energy and therefore most likely decrease the crack propagation rate. And what is wanted in aerospace is to have a very conservative approach in order to make sure that you have the worst case scenario at hand. So in order to know more about this, you can refer to the short course on partition of unity methods and free boundary problems, and where we discuss how to essentially go around the problem of meshing the cracks as they propagate. So there are many approaches which we talk about, including finite element methods, extended finite element methods, mesh-free methods, boundary element methods with isogeometric analysis, which is here. And this is something that needs to be done in detail, which I refer to the course on partition of unity methods. Similarly, in the course of partition of unity methods, we talk about goal-oriented adaptive methods, which allow you to refine the mesh locally around the area where you think the crack is. So before these methods were incepted, so during my PhD, what people needed to do is you needed to actually put a crack somewhere, and the mesh in the whole region where you thought the crack would propagate had to be pre-generated in a very dense manner. So you had to have very many elements in the whole area volume where the crack would propagate. This is of course very inefficient, and this is also quite brute force. So the idea of using adaptive computational methods is that you start with a crack as dictated by the design codes, but the mesh is only refined in the vicinity of the crack. It is not refined everywhere. And as the crack propagates, the crack leads to the refinement of the mesh only locally around the crack front, as you see here, not everywhere else where it's not needed. And the novelty in what we did compared to what other people did is that we targeted the stress intensity factor. We did not target the energy, which is meaningless, but we targeted the stress intensity factor, which is the crack driving force. This is what is going to allow the crack to propagate or not if we reach the critical stress intensity factor, and if we are under fatigue conditions, it is going to allow it to propagate at a certain rate, because as you know, and as you can see in the short course related to fracture mechanics, the amount by which the crack grows in methods such as Paris law, in models such as Paris law, is directly proportional to a certain power of the stress intensity factor. And we saw at the time that if the stress intensity factor is computed slightly off, then the whole crack propagation path can be wrong, because each increment will be off and you cannot heal the crack. So once you've made a mistake in the propagation, we have a history-dependent simulation which cannot be cured. So this is very important. Think about error estimation and adaptivity with a goal in mind, as opposed to doing simply adaptivity using, let's say, the energy as a target. We also talk in the partition of unity method about the extended finite element method, which is one of the ways that you can discretize fractures. And we also talk about the fact that if you have multiple cracks, like here 300 different cracks, the idea would be to try to figure out which crack should propagate in order to maximize the energy release globally. So you would like to minimize the potential energy in the best possible way. To do that, you don't know which of the 300 cracks should propagate, so which of the 600 crack tips should propagate. So the work of Dennis Sutula, which I explain in the partition of unity course, is clearly showing how to do that systematically for as many cracks as you like in a very nice and beautiful way, all implemented in MATLAB and available for free. And that led to extremely nice results. We also talk in the partition of unity course on the comparison between energy minimal fracture and phase field approaches. And we talk about the fact that we can look at arbitrary materials that can be also inhomogeneous. So this is now the first step into inhomogeneity. What you see here is a solder joint that's used for printed circuit boards. You can imagine that current is going to flow from the top to the bottom, for instance. And this is a tin silver copper alloy. And these tin silver copper alloys make polycrystalline grains. They have grain boundaries. And typically the grain boundaries are the areas which are the weakest. So they are the areas where the cracks will tend to propagate. So this is why, in that case, we have a model where the cracks initiate along the interfaces. We compute the damage around the interfaces, and when the damage, due to mechanical thermal fatigue, increases beyond the threshold, we crack the whole grain boundary. And then we look at the propagation of the cracks, and what happens is that at some point a crack will grow, and all the small cracks will coalesce, and the whole grain will be the whole solder joints will be failed. And now what happens here is that we have one solder joint and we have all the grains taken into account explicitly. On a printed circuit board, you have hundreds of these solder balls that are here, you have hundreds of them. And what we would like to know is when they will fail, because that can lead to electric defects in the car. And due to the car starting and stopping several times a day maybe, and the cold climate, so they start at cold temperatures and they heat up at high temperatures, and they do that several times a day. These solder joints can fail, and when that happens, then you have red lights lighting up on your dashboard. So the question is, when is that going to happen? And note, this is very important, that here the grains are of the same sort of order of magnitude in terms of size as the structure. You see here the structure is not much larger than a grain. You know, a grain is here, so you have maybe 5 grains in the length and 3 grains in the vertical direction, depending on the grain size. And that's very important, because that means that here we have, and this is a keyword that I will use today for the first time, we have no scale separation, because all the grains have a size which is similar to the size of the structure. There are cases where there is complete scale separation. So for example, here, if you look at the new materials that are used in aerospace, you can see that the materials are made of extremely small particles, for instance, of continuous fibers or discontinuous fibers or whiskers, or they can be braided, they can be made of fabric and so on. And they are very efficient because they allow to save a huge amount of fuel, as you can see. 1,000 kilometer saving of approximately 9 tons of fuel, and that therefore reduces the weight of the structure by about 20%. So that's quite significant, and that's very good. However, it's also problematic because these materials we don't know as well as the materials that were built before, as for example as aluminum, which I worked on during my PhD. Now people started using these materials before they were actually known, which led to quite a number of difficulties in design and also some failures. For example, people had not thought that there would be a problem related to hygrometry. So if there is too much water in the atmosphere, for example in Hong Kong, the Airbus A380 cannot stay grounded too long because there is some sort of swelling taking place in the material, which then can lead to fracture. So this is something that people had not foreseen and that they had to take a look at later, which led to quite a number of problems of fatigue in these types of materials. And this is a problem that's still now under investigation. So now, I just convinced you, I think, that there are different types of multi-scale approaches. There are some problems where the size of the microstructure is similar to the size of the structure. So that would be, for example, the solder joints that I showed. But there are other cases where it's not the case. For example, here, where you have a bolted joint, 50 millimeter bolted joint, 100 plies, 125 microns per ply with nanoscopic fibers. So if you look at this particular case, you have an heterogeneous multifunctional material, and you need to have a certain number of experiments, similar to Paris law, in order to be confident that the coefficients of Paris law that everybody uses, C and M, are correct. Thousands of experiments were carried out. So here, in order to gain understanding about these bolted joints and these materials that we built, a lot of experiments and numerical simulations are also required. So how can we do that? Well, one of the problems is that we have quite a different environment in real life than we have in the lab. It's quite difficult to reproduce the environmental conditions. So those are quite difficult problems to solve. The second problem is that factor of safety approaches, which basically mean, let's say that we computed 10,000 flights for the Airbus. Since we computed 10,000, we put a factor of safety of 2, and we will say it's not 10,000, but 5,000. So we are conservative, we try to decrease the risk, right? So this is what you typically do in engineering when you don't know something. What you do is you lump all the unknowns into what's known as a factor of safety. Also known as probabilistic-based methods, but these things cannot handle unknown unknowns because there are things you don't know, but you don't know. For example, the fact that you will maybe have some sort of storm. You don't know that exactly when. You don't know the hygrometry. You don't know the temperature exactly. You don't know the wind patterns. You don't know everything that goes around the plane. But there are many things you cannot guess. Because the airplane maybe will be flying in environments which you have no idea about. It can actually be even easier to understand if you think about aircraft that go, spacecrafts, that will go in, explore the universe. Because in that case, you do not know what is going to be found there because you've never been there and you really don't know what the conditions will be in terms of cosmic radiations, in terms of atmospheric conditions, in terms of corrosion, in terms of bacteria, in terms of viruses, in terms of even temperature, in terms of very simple chemical reactions that can take place there. So it's very important to realize that the more you can guess, the better, but it's even better than not to guess, but to put sensors on the structures. And the question is which sensors, in order to be able to make proper designs. So now let's look at numbers. Let's look at numbers. If you take a bolted joint from an Airbus A380, for example, so you have a mixture of metal and these carbon fiber composites which are here. And when these things fail, this is what it looks like. So not very nice. You have delamination, debonding, you have the fibers that get loose and get pulled out of the matrix. So these things are extremely negative, of course, and they are detrimental to the life of the structure, so you would like to be able to predict this. So let's just look at a brute force calculation of this bolted joint. How many degrees of freedom do you think that's going to require? Well, let's look at just a few plies. Let's assume that you want about 10 elements per ply. That could be an overshooting, but let's assume that. If you assume here that you have a 50 millimeter bolted joint, so it's about 2,000 elements. Let's say that you have 50 millimeters per 50 millimeters times 100 plies in the thickness, which is typically what you have. Well, in the end, you get 2 billion elements. So 2 billion elements is something which is solvable. You can solve that on supercomputers today, if you have the proper code, of course, that goes without saying. And it would be also needed to have a fully parallel code using MPI and domain decomposition and so on. That was the PhD thesis of Pierre Kerfeden at LMT Cachan in Paris, École Normale Supérieure. But this is, I have to say, a bit brute force, right? So what you'd like to do is you'd like to reduce this complexity. So you'd like to be able to solve such problems in a way which is much faster. So this is the PhD thesis of Pierre, as I was saying. What he did is he was dividing all the plies into sub-blocks, and each block was sent to one CPU. So you can see, I think in this case he had something like 450 or 512 CPU, if I remember correctly, and he could solve that in 1 week at the time. So in 2009. So this is exactly the problem we're trying to address today. How do we deal with large structures whose behavior is governed by small-scale effects that lead to intractable problem size? This is the question that we would like to address today. And again, we will do it via two ways. One will be algebraic-based, model order reduction, artificial intelligence, machine learning, and on the other hand, it will be done using mechanics and physics-based only. Here's the question: how can we reduce the problem size but keep the accuracy under control? So how can we do this? This is really the question that we need to answer. So the first thing is that we have a certain challenge. Okay, we want to preserve certain features and we want to reduce the problem size at the same time. And that will allow us to reduce the computational expense and therefore control the error. Okay, so again, we are today going to talk about two approaches. On the left-hand side, you see that we are going to talk about approaches known as multiscale methods, and that can also be decomposed into at least three categories. And the right-hand side is going to be machine learning, algebraic-based model order reduction, proper orthogonal decomposition, and so on and so forth. So I just would like you to remember this. We will talk about two approaches. One is physics-based and the other is, let's call it machine learning based, but we could also call it algebraic based. And let's understand why there is a nice monkey on this picture. But we will do that after we have talked about physics-based approaches. In the next part of the talk, I'm going to convey to you what means lack of scale separation, and I'm going to do it from both the reduced order modeling and from homogenization, meaning the physics-based approach. And I'm going to link these two together. Remember in the course on how to create a mathematical model and how to discretize and how to control the discretization error using a posteriori error estimates and the model error using appropriate models for the problem that you're solving, and trying to address the question, are we solving the right problem? And the verification question, are we solving the problem right? Meaning, are we solving the PDE properly? Is it converging? Is the solution accurate enough? Can we capture the discontinuity or the singularity in the solution? That's the discretization error. And the model error, what is the question to the validation? Are we solving the right problem? So today, which of the two questions do you think we are asking? We are talking about multi-scale approaches. So we are mainly asking, well, we are asking the model error question, because we don't know whether we should have a model at the coarse scale only, like for unidirectional composites, thesis of Lisa Cahill that I showed before in the fracture mechanics course, and we don't know if we need to take into account all the grains, like in the solder joints, explicitly, all of them. Or we don't know if we could maybe do some averaging and have a few grains taken into account and then use homogenization to do it. So that we don't know. And this is the question we are trying to address today. So to do that, we're going to look at the first class of methods that I call physics-based model reduction methods. And I'm going to explain why I believe that the name physics-based makes sense. First of all, let's look at a typical example. So that here is a polycrystalline material. So that could be steel, it could be aluminum, it could be any type of alloy that you're interested in. And the question that you're asking is, how can I simulate the full scale problem with all the grains? Remember the case of solder joints for the printed circuit boards? Well, you had a few dozens of grains in the whole structure. And look at now this case, where you have maybe hundreds of thousands of grains in that structure. And ask yourself, how am I going to solve this problem? By taking explicitly into account all the grains, knowing, and this is very important, that each grain here that I choose, each grain will have different properties to the neighboring grain. Point number one. It will be anisotropic. It will have a specified direction which is of interest, and only of interest to that grain. The neighboring grain will have completely different properties. It will have completely different fracture properties. It will have completely different dislocation dynamics. It will have completely different Young's moduli, so elastic properties, Poisson's ratio in different directions, so stiffnesses will be different. Temperature parameters will be different, coefficients of thermal expansion will be different. So everything will be different in these little grains. There are no two grains in there that are the same. They are all different in shape, different in material properties. And not only that, that would be too simple, but if you keep zooming, you will see that there is an interface. And this interface between the grains will also be different for all grains. So there are not two interfaces in there that is the same. So you can imagine the problem complexity of dealing with hundreds of thousands of grains with dissimilar interfaces, dissimilar material properties at each grain, and doing that on hundreds of thousands of grains in one structure. And we're talking about 2 dimensions. If you think about several dimensions, like 3 plus time, then you immediately understand that there are some severe difficulties in dealing with that. So this is what is meant by this sand clock, and I think this is really amazing, because when you look at that, you really wonder, how am I going to even work on that and find a solution? So let's look at possibilities. Now we see this problem. This is, let's say, an L-shaped problem as it's known. And we just agreed that solving the problem with hundreds of thousands of grains with dissimilar properties for each grain is going to be totally out of scope, out of reach, and that we cannot do it. That's our assumption. Of course, you could disagree with me and you could tell me that there are some computers and some codes that could be written in order to solve that problem, and I would probably agree. It's not really totally impossible. The only problem is that it's so computationally intensive that no one would like to use this method. When you want to design an aircraft or want to design anything, you don't want to wait for 2 weeks to be able to get one solution, which, by the way, is only one statistical representation. And this is a very important remark that we should always keep in mind. When you look at this particular piece of material, not only do you have 100,000 dissimilar grains with dissimilar interfaces between the grains, but also this is one representation of a possible microstructure, but this is only one. And in order to be statistically meaningful, you would need to run sufficiently many statistical versions of these microstructures. So you would need to run many instances of this microstructure in order to be predictive. Because it could be that the grains that are located here at the corner will have a huge influence on the propagation and initiation of the cracks. So if you run only one test case, you are not taking into account the full statistical variation of the microstructure. If you remember the solder joint case, that was also the case. I showed you one instance, one representation, one statistical draw of a possible microstructure, but you could have had any other, and that would have probably drastically changed the simulation results. So this is something that really needs to be taken into account and really firmly anchored in the brain of people that are working on multi-scale methods, because what happens, and which is very important, is that the microstructure is one microstructure among many possibilities. So multi-scale methods are intrinsically linked to statistics. So now you would like to replace this particular microstructure by a PDE, so partial differential equation, with constant coefficients. So you see here, big problem. Here everything varies all the time. So if you were to draw some sort of variation, so if you take a line from the left to the right and you draw variations of any of the properties, then you would see a huge amount of variation. It would jump up and down constantly. Now what you want is you want one PDE with constant coefficients in there. So of course that is the main difficulty of multi-scale approaches. So how do you do that? Well, the thing is, you try to replace the heterogeneous nature of this problem by something which is smoother, and you do that at the scale where the predictions are required. So for example, you would like to just send your simulation in a computer, go and take a coffee, come back, and boom, you have the solution. How do you do that? Well, the idea is that at each material point in the structure, which is here written, at each material point you will have one point which is represented by another volume, which is supposed to represent what happens at that material point. Which means if you go to another point, you will have another volume which represents another material point. And it's possible, and very likely, that these two volumes that are supposed to represent what happens at that point be different in terms of numbers of grains, size of grains, interface conditions of the grains, material properties of the grains, and so on. So you can have full variability, but now instead of having these grains exist everywhere in the structure, you compute averages at material points in the structure by performing integrals over this representative volume element. And this is the first time today that we use the word representative volume element. I will not even define it very precisely today because there is a large amount of literature about how to define representative volume elements, but I will give you enough information so that you can understand and read the literature. So now, I'm going to talk to you about various methods you can use for simulating problems that have multiple scales. And I will start with the first method, which is the most easy to understand and is also the most natural one. And these methods are called concurrent methods. So the concurrent methods have two scales that coexist in the domain. A fine scale, where you have, for example, all the fine scale details that you're interested in. So you're talking about grains or about cells, or you're talking about fibers and lamina in composites. So all the things you're interested in here are explicitly taken into account. And everywhere else, meaning beyond this dashed line here in the domain, nothing is taken into account explicitly, and you are dealing with an homogenized or average material, as we said in the previous slide. So as in that slide, you are here taking into account one material point, which is the average of what takes place at the smaller scale. So here, in some region, you have a full description of the microstructure, and in other regions, you don't. So this is known as concurrent methods. And the difficulties in concurrent methods, you guessed it. What would you think the difficulties are? Well, yes, the difficulties are the interfaces between the two domains. And why is that? Because you need to make sure that you keep continuity of the field variables across these two different representations of the domain. You see, here on the left-hand side, you have to deal with a continuous and constant coefficient PDE. On the right, you have now discontinuities through the grains, and you need to take care of having a continuous transition between the two. Otherwise, you would create a jump in the displacement field, which you don't want, and a jump in the strain field, which in that case you don't want either. So if you create jumps or incompatibilities between the two domains, depending on what problem you're solving, you are not addressing the problem properly. So you need to make sure that that works. The second problem that you can have at the interfaces, and this is looked at in detail by papers by Bilichko and others at the time, in methods known as the bridging scale method or the bridging decomposition method, where he's trying to merge two domains. In his case, he has a mesh-free domain on one side and a finite element domain on the other side. And he's sending waves that are propagating from, let's say, the mesh-free domain to the finite element domain. It turns out that the mesh-free methods are smoother, so they are softer than the finite element methods, which are more rigid. And this is an aside, but that leads to wave reflection. So if you have a wave that comes from the soft domain into the stiff domain, the waves will reflect as if they were hitting a wall. And vice versa, if you go from the stiff domain to the soft domain, things will work seamlessly. So there was a problem of trying to enforce the conservation of energy, not only the conservation of the jump properties along the interfaces so that you don't create artificial jumps and discontinuities in the variables you're interested in, but also that the energy that is being transmitted and transferred from one domain to the other be kept constant. So there are lots of methods on this that I will discuss in future lectures, in particular in coupling molecular dynamics and finite elements together in a way which preserves the energy. But today it is enough to know that we are going to talk about how to couple these two interfaces together and what are the main difficulties associated with that. So if you want to look also at some details, there is a paper by Ahmad Akbari in Philosophical Transactions, which you can take a look at, and that will tell you a little bit more about what that means. And if you are even more interested in details, I will post in the video a link to the papers that were written by Ludovic Newells and also Timon Rabchuk in Advances in Applied Mechanics, which I'm editing, where there are a lot of details. So these papers are 200-page long, and they give you a huge amount of details on how to handle multiscale methods. And I think there are a wealth of information that can be taken a look at. I will put that in the comments. So these are concurrent methods, as I was saying. So you have an interface that you need to take into account. And you have a coarse scale zone and a fine scale zone. And in the fine scale zone happen all the things that you're interested in. For example, crack initiation, crack propagation, and so on. So I think this is extremely useful to know. As I said, this can be done for molecular dynamics as well. So here you have a fine scale zone. And this is reported in the paper by Talibi, Ramaya, Rabchuk, Bordas, and Kerfreden in 2014. Now, 9 years ago, and what we did there is we had a molecular dynamics region, which was coupled to a full finite element region, which you can see here. And what was happening is that the crack was propagating in the molecular dynamics zone, which allows you to use a full-fledged molecular dynamics approach in order to initiate and propagate the cracks. So it's very desirable. Of course, much more expensive. So similar to the coupling between mesh-free methods, where you have particles, here you have molecular dynamics, so you have atoms. The connection between atoms and particles is quite close, so you can think about them this way. And then you have an interface where you attempt to conserve energy. This is the main point. And then once the crack has propagated, the idea is that you do not want to keep all the particles, all the molecular dynamics atoms behind the crack wake. Because behind the wake of the crack, you don't need all these atoms anymore. Nothing is going on. Once the surfaces have separated, the potential energy here is not important anymore, so you can just get rid of the particles and you can coarse grain. Coarse grain means go from small scale to large scale. So fine graining is the opposite. You go from coarse to fine. Okay, so now you are coarse graining, meaning you are starting from molecular dynamics to a jump. So the question here was, how do we compute the jump and how do we impose the jump back on these elements that are here that used to have only these molecular dynamics approaches, and now that we need to overlap. You can think about the link between this method, and maybe it came to your mind, and to the material point method that I introduced in the course on material point method with Yunwin Fu. And if you take a look at that, you can imagine how we perform the interpolation and extrapolation between the particles, meaning the atoms, and the mesh. So that's something that's worth thinking about. Again, it's in this paper, and we show how things work. So that was for concurrent methods. That was a very short introduction, and I will do another lecture with more details on this. So this is only now to show you what you can do in terms of not concurrent, but now semi-concurrent or hierarchical methods. So let's try to figure out why it's called hierarchical methods. So the idea in hierarchical methods is that you have one domain which speaks to another domain. So there is a hierarchy in the domains. There is a domain at the coarse scale, so large scale, and there are domains at the fine scale, like the representative volume elements. And the question is, how do you link the fine scale to the coarse scale? And so this is how it's done. Let's imagine that you have a mechanics problem at the coarse scale, so you have finite elements. And let's imagine that at each of these points in the elements, you can think of them as integration points, so material points. Each of those points is now associated with a representative volume element, which on purpose I did not define properly because this is takes a long time to define properly, and it's still subject to discussion. But suffices to say here that you have a representative volume element, meaning that this is the smallest possible volume which represents the statistical variability of the fine scale. Meaning if you take it larger, it is too large, and if you take it too small, you do not see the statistical variability. So for example, a typical representative volume element could not be smaller than 1 grain, or an aggregate in concrete. It will need to handle at least a few aggregates and some of the cement paste, such that you have a good variability in the aggregate size, that you have at least a few aggregates, and that you have at least some of the cement paste. So that sounds like heuristics, and it is, but in reality you have some very clear tests to make sure that the representative volume element is indeed representative, and to know when it's too large or not too large, right? So this is really the key point. And now, what is the algorithm looking like? So typically, if you are here in a mechanics setting, you will compute increments in strain. So you can think of an elastoplastic material. You will have a way to compute a change in strain at each increment. So you will increase the load, for example here, delta F. That will lead to a change in strain, delta epsilon. That delta epsilon now is computed at each integration point and will be applied now on the boundary of this representative volume element. You will apply this as a displacement field on the boundary by simply computing the displacement from the strains. There is a way to do that. And then you will solve a finite element problem at that scale using the boundary conditions given by the strain field, which is computed at the coarse scale. So you will now have another finite element problem, another mechanics problem, which you solve at that scale. So if your problem handles mechanics, that will be grains, or that will be fibers or interfaces and so on. If it handles biological materials, it would be different cells that you compute here, on which you will apply some material and some boundary conditions and some initial conditions. You will solve that problem whichever way you solve it. Could be also with agent-based, why not? Although this theory is not well developed yet. You will get a solution. What does the solution look like? Well, you applied a strain, you will get a stress back, right? And you will get also a material stiffness, which is the tangent stiffness, CT. And that's good, because you can imagine, exactly as in other instances such as plasticity, where you have phenomenological models. Remember the course on the data-driven journey. We said at the beginning that there are some phenomenological models of plasticity that talk about void coalescence and growth, von Mises plasticity, for example. So you can imagine that here, if you were to model von Mises plasticity at the representative volume elements scale, you would have these voids. These voids would actually grow and merge. And depending on how they grow and they merge, they would give you a sigma. And you can think of this loop here as a numerical version of a constitutive law, a numerical version of a mechanistic constitutive law, which is no longer mechanistic because it takes into account all the details that you need at the fine scale, or at least all the details you think you need. You see, so the idea is that you do not assume anything about how sigma depends from epsilon, except based on how the microstructure looks like. You do not have anymore a functional form that gives you sigma c equals function of epsilon c. What you have now is you have a whole partial differential equation in a quite complex domain that is being solved, and that gives you sigma c and the tangent stiffness every time you pass epsilon c to the RVE, which is done at each integration point in each element of the coarse scale finite element domain. So that's the key about hierarchical methods. And now we're going to see when hierarchical methods break down, because of course they do. All methods break down at some point, and we would like to see how it works. So the first question is, what happens? So here we have two axes. We have sigma c and epsilon c. C stands for coarse, because we are living at the coarse scale at point x in a finite element at the coarse scale. And what we are drawing is the loading of this element. So we are considering only one element that contains one point x, and at that point x we are increasing the load. Or you can think of, we are increasing epsilon c because we are computing at this element the displacement field at the three nodes, u1, u2, u3. Based on the shape functions inside that element, we are computing the strain field at point x. And based on that, we are passing the stress field to this representative volume element and computing the stress field. So we are passing the strain field computed by shape functions, and we are computing the stress field and the tangent stiffness. And the displacements on the boundary of this element are varying because we are increasing the load. So we may start with a small load of 0, then we increase the load, and we will follow that curve. And what we are doing basically is drawing the stress-strain curve for that point without having any analytical formula for the stress-strain curve. If you take into account elasticity, the stress-strain curve will be a line. If you take into account plasticity, it will probably do something like that. If you unload, it will unload linearly and then come back. And you normally use analytical models. But here we don't use analytical models because we don't have analytical models. We have only what we know, which is the microstructure. And we use that to come up with this cycle, which gives us the response in terms of stresses if we know the strains. So we keep loading, and we end up there at that new point, sigma versus epsilon. We keep loading, we end up at that new point. So we keep increasing here the loading on that edge, which increases the displacement on these three nodes. And we keep loading, and at some point we reach a peak, which means the highest stress that that particular point can see. And that is due to the fact that in these RVEs, you may have fractures, you may have damage, you may have all sorts of problems taking place. You may have irradiation and some dislocations forming, or some atoms missing, or some atoms actually being completely thrown out of the lattice. And so you end up at a peak. And this is where the problems take place, because you have now a material stiffness tangent, meaning d sigma c, d epsilon c, so partial sigma, partial epsilon, which is now negative. And why is that a problem? Well, because you are solving a partial differential equation here, which is an elliptic equation, which means that certain coefficients need to be positive for that equation to be elliptic. And now that particular coefficient, which is the stiffness, is no longer positive, it's negative. So this is really nice, because you can see that you have a way to figure out when the material fails. If you're interested in this, I very highly encourage you to read the book by Ray Ogden, because Ray Ogden has, in chapter 5 of his book, Nonlinear Elasticity, a very detailed description of loss of material stability according to the acoustic tensor. If you also are interested, I will give you references on mesh methods by Ted Bilichko, because he came up with ways to initiate cracks using the acoustic tensor, and we, with Timon Rabchuk, worked on that in 2007 in a few series of papers on element-free Galerkin methods, where we initiate the cracks using similar approaches. So I think it is something which is really pervasive in the whole literature, both at the material level and at the computational level. In any case, what happens here is that what you would like to do at the coarse scale is you would like to introduce a crack, because you are starting to damage the material. So at the coarse scale, you would like now to fail that element. The problem is, how do you do that? Because if you don't do anything, when you have this let's call it localization, here you will have localization of strains. And if you don't do anything, this element will damage. And unfortunately, your results will be mesh dependent. Because if you refine the mesh, the element will also damage, but now it will be a smaller element. And therefore, you will localize in a smaller element. If you refine the mesh again, you will localize in yet a smaller element until the element size goes to 0, and the localization happens in a set of measure 0, an element which is infinitely small, and therefore the energy that you damage the material with, so the energy that you dissipate is now 0. So you dissipate no energy, which is contrary to physics. So therefore, you need to have a way to so-called regularize, and this is a whole theory in multiscale methods that we will cover in forthcoming courses, where you can regularize the problem, meaning that you can dissipate energy over a set of measure non-zero, which is due to a length scale of the material. So you will introduce a new length scale, which tells you over which domain you can dissipate energy, meaning that if you keep refining the mesh, all that will happen is you will have more elements in that domain, and you will keep dissipating energy. So this is a bit of a technical part, which is extremely important. So when you localize, meaning when you reach the tangent stiffness, which has a negative slope at the top of the peak, when that happens, what happens at the core scale is that you have now a localization here. So you will have damaging material. When that happens, you need to find a way to regularize, and usually it's done by either a non-local model or a gradient model, or some higher versions of this, or you can introduce a cohesive crack directly here, which dissipates the amount of energy that you are dissipating. So you will introduce a crack, you will look at where you are on the down-going part of the curve, and this energy below the curve, you will initiate a cohesive crack with. And for that, I have, with Timon Rapsuk, a very, very nice description in computational mechanics in 2007, that I can refer you to because it gives all the details and it's very didactic. And so when that happens, you have two possibilities. As I said, you can introduce a crack at the core scale that regularizes the problem, meaning it avoids dissipating energy over a set of measure 0, meaning dissipating no energy. Or what you can do is come up with a hybrid method where as soon as you reach material stability, which is the peak here, so you reach instability, as soon as that happens, what you do is extremely simple, but at the same time simple conceptually, but very difficult to implement. You replace the elements where you reach the peak by one representation of the microstructure, one instance, one statistical draw. So you throw some dice and you say, okay, here I assume that microstructure looks like that. And then you continue the calculation. It's not as easy as saying then you calculate, because as you can imagine, sorry, here on the interface, things are not that trivial. Why? Well, because you started here with one element that has a whole history of loading. You know, the integration points here, they were loaded up to that point, and they went through plasticity, they went through a lot of time-dependent variables that now, if you have to replace those by grains, you essentially need to reload the whole granular structure here in order to allow that granular structure to live the same life as the integration points, the material point that was living here before. So you need to reapply the history of that material point to these little grains so that they have the memory of this material point that was there before. Otherwise, they will have no memory, they will be unloaded, so you would introduce them here, which is completely wrong because you reach the peak. So you want to reload all the microstructure here until you get to here, which is a very difficult thing to do because you need to unload everything and reload everything now with the real microstructure in here, which is extremely computationally intensive and would need to be accelerated, maybe using methods such as machine learning. So this is still a very open area of research, which today still leads to researchers and engineers scratching their heads day in, day out to try to figure out ways to do that properly. And now what we're going to do is we're going to look at a few examples. In multiscale methods, there is another keyword which I will introduce now, which is known as direct numerical simulation or direct numerical solution. What that means is that instead of using the reduced version, meaning the multiscale version, you will now use a full detailed model. So meaning you put all the grains there that you think are in this area explicitly in, and this is what you use in order to make the simulation, as opposed to doing what we just said, meaning to have this adaptive multiscale approach where when the elements have failed because they have reached a peak, you replace them by the full instance of the microstructure. So this is essentially what we are trying to do here. So let's now try to understand how you can compare these two approaches. So we will take that particular region, apply loads, and based on these loads, we would like to figure out what the deformations will be like. And we would like to compare the energy dissipation and the force displacement curves. Also, important, we have 20 to 100 times fewer unknowns in 2D and 3 orders of magnitude fewer unknowns in 3D. Well, that tells you quite something. So in terms of complexity, I think it is very important to think about that. Okay. So now what happens if you take first a very simple example known as uni-axial tension. So that's going to be very simple to understand, and this is what I would like to show now. So we have a notch in a specimen which we are pulling upon, right? So sizes are in millimeters, so quite a small specimen, and you have here a notch. Again, quite a small specimen, something that's quite usual in computational multiscale methods, because looking at large scales is often very difficult. And so the more detailed the model is, the more difficult it gets. So the idea here is look at von Mises stresses in the region where the cracks initiate. So we initiate with no crack. The cracks initiate only when we reach the peak. And when we reach the peak, we let the domain propagate. And as you can see, the elements where the full microstructure is being taken care of is moving through the domain and is taking more and more of the domain space. So now the crack is like that and takes into account the full microstructure. So there are a few caveats that I would like to tell you about here. The first one, which is extremely important, which I already mentioned before, is that here we made one choice of the microstructure, one instance and one instance only. So we could have thrown the dice and found completely different microstructures. And therefore, the simulation would have been completely different. Meaning that if we want to have really a predictive model, what we need here is to have a stochastic simulation. What we would need to do is to do a Monte Carlo simulation where we choose a microstructure every time, a different one, and run the simulation to find a crack propagation path and to find the energy dissipated below the curve, so the force displacement curve. So that is a given, and this is extremely important. And I don't think many people talk about it very explicitly in the literature, which makes you think that when you do one calculation, this is the calculation that you need to make. But this is wrong. What you need to know is that the calculations that need to be done here need to be done every time for a different microstructure in order to be predictive. And think about it. It is extremely difficult to do because we're not only talking about the geometry of the grains, we're talking about the material properties of each grain. We're talking about the material properties of each of the interfaces between the grains, about the size distribution, about where the grains are, and so on and so forth. So this is not something that is trivial, that you just click your fingers and you can make it happen. So I think there is a lot of work needed here in order to accelerate such simulations and create new approaches which will be able to do these simulations fast enough and take into account the full statistical space in which we are generating these microstructures. So what we did here is really a toy example. I'm very proud of this work because Ahmad Akbari and Pierre Kerfreden and myself worked very hard to make it happen, especially Ahmad in the coding was extremely diligent, and the work he did here is outstanding. However, it is still a toy problem. If we want to solve real problems with real statistical variability, there is still a lot to be done. Another thing that is important to realize is that the cracks are propagating, but at some point, similar to molecular dynamics cases, you don't want to keep the atoms living everywhere in the domain because this is super expensive. Here we are keeping all the grains where nothing happens. If you see the colors, all the red is taking place here at the crack tip. Nothing is going on here where we are only unloading. So, in the curve, we are now here. Sorry, we are here. We are still loading, but in that area here, we are close to the peak, right? So we are here. So again, remember, some areas of the domain will still be loading when others will be unloading. Some will be reaching the peak when others will be starting to load. So all this is made possible by this beautiful method. However, there is a lot to be done in order to make the methods really tractable computationally. Okay, and by the way, this whole theory comes back from Fayel and Chaboch in year 2000 with the finite element squared. This is the name of the method, and this is Fayel and Chaboch that came up with this method in year 2000. Okay, so now what is the major approach if we summarize everything that we've said till now? So let us summarize. We start with a semi-concurrent finite element square approach before we reach the peak. In some cases, you may even start with what is known as analytical homogenization, which we haven't talked about yet, which boils down to computing average parameters for structures, right? So you compute everything by hand. You do not need to compute anything numerically, which is numerical homogenization. Analytical homogenization requires only hand calculations based on averaging, theories of averaging like Mori-Tanaka scheme and so on in micromechanics. So you can do that first, as long as there is no change in the microstructure. So for example, if you have cracks that are taking place, or if you have dislocations or damage taking place, the analytical homogenization is no longer possible. You need to move to numerical homogenization, computational homogenization. This is the way it's called. And this is known as semi-concurrent. So you start by analytical, maybe, if nothing happens in the microstructure. As soon as the cracks start to appear or damage takes place, you see that you need now to have a semi-concurrent approach. Why? Because all the points are behaving differently. So if I take a point here, nothing happens. So we are still loading. Analytical homogenization is enough. But if we are now close here to the L-shaped corner, we know that we'll have stress concentrations there. So most likely we will have damage taking place, accumulating, fractures initiating, propagating, joining, merging, coalescing, and so on, before we reach the peak. And when we reach the peak, this whole semi-concurrent approach goes out the window because, in fact, we lose separation of scales. And the reason why we lose separation of scales, which is also quite difficult to understand from the literature, and I think the best person in my team to talk about this would be Lars Bakes, who worked on the quasi-continuum method, and he's very knowledgeable in this. When that happens, what you do is you lose material stability. You have localization, and therefore you have to switch to concurrent methods. And the reason is that you can imagine that if the crack propagated through and through this representative volume element, splitting it in two, well, the boundary conditions that you used to apply here, which typically are periodic, are no longer periodic because you are splitting them using a discontinuity, for example. So you cannot continue the simulation, and you need to switch to a concurrent approach, which is what we did here. in this paper with Ahmad Akbari. And so this is basically what happens. And then as soon as you've switched, now you have some new elements that are created with one instance of a microstructure. Again, this should be done for an arbitrary microstructure, and this is very time consuming and very challenging. And that's it. So now the open problem that we have here is really model selection and error control, because in what I just presented, we have an approach to first refine the mesh. So we first solve the problem of assuming that everything is analytically pre-computed. So here, analytical homogenization. We refine the mesh close to the singularity using an a posteriori error estimate, as I presented in the courses on a posteriori error estimates. So we refine the mesh here. And when we get too small in terms of element size, and we get close to representative volume element size, so for example, close to a grain size in terms of the element size here, then we switch to a semi-concurrent approach. And we switch to a computational homogenization, and every time we reach the peak, we switch to a concurrent approach. So that's the idea. So the problem is to do that systematically. And what we could probably do is to use machine learning and statistical inference, and that we could talk about in further lectures, because we have some recent results that are in this direction. Another open problem that I mentioned, and I want to mention again for the third time, is the statistical variability at the fine scale, geometry, material parameters, and so on, which are definitely to be taken into account. And so there are different things, because we have a statistical variability. First question is, how do we identify this variability? How do we know what the material properties are? This is not so trivial. And the second question is, once we have identified that through small-scale experiments, we can use Monte Carlo analysis, meaning we can throw some dice and use the probability distributions for the material parameters that we have identified in order to solve the problem multiple times. So I think that's basically what I wanted to say on these physics-based computational approaches. Now I'm going to tell you about ways to reduce these problems using algebraic model order reduction, which are based on pre-computed solutions, pre-computations, in order to accelerate what are called online simulations. Online means when you want to make the prediction. Offline in this jargon means before you want to make the prediction. I will make that clear in the forthcoming slides. So let's first give a few examples on what that means. So we will assume that we have parametric problems, meaning that we have a problem that we're trying to solve, which is governed by a set of parameters. So let's imagine that this problem is like this. We have a lattice beam problem. That means that each of these little bars here is a beam. It's a beam element, and it can damage. And the problem is that you do not know what will be the load that the client, let's imagine you are in a design office and you are trying to design this beam, but you have no idea what load the client will give you. Meaning that they will come to you with some sort of loading that they come up with using their own methods, you don't know about it. And they will come up to a load maybe here of 1 meganewton. That's it. That will be the load, but you don't know what the load will be. And you know this client is going to come next week. And they will give you the load. And when they give you the load, you will have 1 hour to compute the solution. But you know, here, of course, the problem looks very coarse and very simple to calculate. It will probably take 1 second to simulate this. But let's imagine, for the sake of argument, that instead of having thousands of beams, we have billions of beams here, that the problem is really huge, like the problem we had before with the microstructure, with tens of hundreds of thousands of grains. Let's imagine that this is a similar problem that we want to solve, And it is very, very, very long to solve. So when the client comes and they give you 1 hour to solve, you know you will not make it because you will need a week. So what are the possibilities? What can you do? The client comes, gives you 1 week to get ready, and after 1 week you will have 1 hour to compute. That's the situation you're in. So what could you do if you were in that situation? Well, you don't know where the load will be. Maybe it's here, maybe it's there, maybe it's here, maybe it's here. So what can you do? You cannot compute all cases because there is an infinite number of cases. So clearly that's not a solution. So one solution that could come to your mind is a bit related to model analysis. So if someone asks you for the vibration modes of that beam, well, you can do some sort of model analysis. So you can do eigenvalue decompositions and try to look at the solution as a combination of these eigenvalues. So you will have a deformed mode like this, have another deformed mode like this, mode 2, and another one mode 3, and mode 4, and so on. And then if you want to look at the vibration of that beam, you know that you can look at decomposition in a modal way. How can we do that in practice? Okay, well, what we can do is we can pre-compute some deformations. For example, you can apply a load F1 at a point and then store the solution S1, which will be the displacement at all the nodes of all the beams. So that can be a very long column vector, okay, because we said we have 1 billion elements. So that vector here will be 1 billion entries. So that's a long vector, but why not? And then we can apply it to another point, FD2, and we get another 1 billion by 1 vector. And we can apply it to other points on the top surface. And finally, we are going to be able to get a matrix which is 1 billion by ns, so which clearly has much more rows than it has columns. And what you would like to do is do an eigenvalue analysis, but you cannot because you did not compute 1 billion loads, but only ns loads, so you don't have a square matrix, you have a rectangular matrix. And so what you will do is do a singular value decomposition, which is a generalization of eigenvalue analysis. And this is known as proper orthogonal decomposition because the modes that you will get are orthogonal to each other according to a certain dot product. And what you do get, so again, if you do an eigenvalue analysis, you know that the first few eigenvalues or the first few singular values are the most energetic ones, meaning they are the ones that are the most important. So that would be C1, C2, and C3. Okay, so you would have 3 basis functions. If you look at their shapes, you would see that they are relatively smooth functions because they are the low order modes. So the low order modes are always very smooth and not very fast varying. But now let's assume that the client comes after 1 week and you have pre-computed all these things, and they come to you with a load which is 1 million times bigger than what you computed. So now you're totally done. You're totally lost because you're trying to use your data that you pre-computed for a whole week of calculations. And this client comes in and gives you a load which is 1 million times bigger, which you could not predict because you couldn't know what the load would be. They gave you no indication. And so now what will happen? Well, what will happen is very unfortunate for you because all the loads, all the modes that you pre-computed will be now totally useless. Because here you have now a crack that took place because the beams that in your case were not damaging, nothing is damaging here, it's all very nice and smooth. Now the beams are broken. You have a kink. So this is not so nice. So the question is, how can you deal with that? How can you pre-compute something when you don't know what's going to be the question that you're asked. Are you going to be asked to compute with a load which is 1 million times bigger than the load that you've computed with? In that case, when you have unknown unknowns, this is when the problems start. Maybe you send your spacecraft to a place where the cosmic radiations are huge, and this is damaging the material so much that it breaks. So this kink, which is a jump in the first derivative, this kink here, well, this kink is not smooth. So you can try as much as you like to superimpose these three modes to get this function. You will not make it because of the phenomena that we talked about in the approximation theory part of the course. We're trying to approximate a function which is non-smooth with smooth functions, and we know that this doesn't work. You will need to use enrichment in order to make that happen. And so, in fact, that's exactly what we are going to do. Except that the enrichment will not be partition of unity enrichment that we talked about in the partition of unity course, but it's going to be enrichment of the snapshot. So the snapshot are these three vectors that you pre-computed for small loads that are applied on the top surface. And now you're given a huge load which breaks everything down. How can you update the snapshot? Well, the thing is, you can update the snapshot by doing other pre-computations. So this is the way that we did it here. There are 3 papers on this that Pierre Kerfreden came up with in about year 2011 and 12, and also with Olivier Goury. So this is a very, very interesting set of 3 papers that I will give you references to a bit later. What we do is we do domain decomposition methods. So why is that actually useful? Well, let's look at it. Now let's assume that the beam is the same beam as before. Now I just drew much more points than were drawn before, right? So we apply a load and we see that there is some fracture somewhere. So that area cannot be pre-computed using proper orthogonal decomposition because that area is not reducible, right? Because it is not in the snapshots, because it has a jump here. And this jump is not something that you want to take into account. You cannot take it into account. So now, if you did pre-computations using a load which is arranged, let's say, at 15 degrees, and another pre-computation at 45 degrees, look at the crack. This crack propagates perpendicular to 15 degrees. This crack propagates perpendicular to 45 degrees. And this crack here, for 30 degrees, your question is, where is the crack going to propagate? And if you do nothing, well, you will simply see a superposition of the 15 degree and 45 degree crack, and that will give you the crack at 30 degrees, which is totally wrong, because the crack at 30 degrees should propagate at 30 degrees compared to the loading that you applied here. So what we do is that we perform this proper orthogonal decomposition everywhere except where there is fracture. So if you have fracture here, in that area you do not perform model order reduction. And I'm sure that now you remember what we talked about when we talked about the breaking down of physics-based model order reduction based on multiscale methods. In the region where you have fracture, you could not do semi-concurrent optimization, homogenization, because you reached the peak. But in the regions where you were far from the peak, you could do homogenization using semi-concurrent approaches. Here the problem is exactly the same. So this is the link that I've been talking about from the beginning. If you are able to understand this link, I think you will really have learned something today. And this is what the slides mean. So you have, in the physics-based approach, a representative volume element that does not exist after the onset of fracture. And in the case of algebraic-based model reduction, the problem is not reducible in the fracture process zone, so close to the cracks. So this is why in both cases, you will have adaptive domain decomposition and adaptive multiscale methods. And so this is basically what you should know about this.